right. My name is Lena Pulkkanen. I'm the director of the Magnetoencephalography Laboratory in the NYU Psychology department. And now I'm going to give you a quick tour of our lab. So what does MEG measure? Well, MEG measures the magnetic fields that are associated with our neuronal activity. So we're going to be visiting the lab with these kids who have participated in our study, and they also are visiting the lab to learn more about MEG and the brain. And so now, just to get started, let's imagine that there's some neural activity, as there should be, in this little boy's brain. And so let's specifically assume that there is a current in his brain that's flowing like this. It's a little arrow that is neural activity, electrical activity, pointing downwards. So now, what you may not know about the consequences of that neural activity is that it's actually something that we can detect outside your head without even touching your head at all. And the reason for that is that if there is a current like this in this boy's brain, it creates a magnetic field that's kind of like rotating around the current. I'm drawing it in a very exaggerated way here. But if there is a current in the head, there is a magnetic field that rotates around the current in such a way that we can capture that magnetic field outside the head. So you can kind of think about it in the same way that when I'm speaking, there are sound waves coming out of my mouth, and if I put a microphone here, I can capture those sound waves. Well, in a sense, what the MEG machine does is it places a microphone close to the head such that we can record the magnetic fields. That's the basic idea. So let's then join this team on the visit. Okay, here we go. I'm going to pause here so we can take a look at this metal tank that is sitting right outside the lab. That metal tank is used to deliver liquid helium into the MEG machine. And the reason that we need to bring liquid helium into the lab is because the magnetic fields that come out of your head that are associated with your neural activity are really, really tiny and very weak compared to all the other electromagnetic activity in the environment. So we need to have a sensor that is superconductive. It's able to pick out that really, really tiny magnetic field. And in order for the sensors, the MEG sensors, to be superconductive, they have to be in super cold temperature. And so specifically, they lie in liquid helium, and that is what sort of helps with the superconductivity. So let's then move on. Here, we're noticing that we're going into a room inside the lab. And this is the magnetically shielded room within which the MEG instrument actually sits. So the MEG machine has its own little house. And the reason why it sits in its own little house, it again has to do with the fact that the magnetic fields that come out of your brain are super tiny compared to all the other electromagnetic activity that's in the environment. So the magnetically shielded room helps us to block all the other noise, the urban noise, from our recordings. So there are several layers of mu metal and other material that block the environmental noise. So very heavy door. Let's take a peek inside. Here you can now see there's a bed, and then there's this tank, sort of the liquid helium tank is inside of here, and then the MEG sensors lie inside the liquid helium. Another way in which we are able to enhance the brain's signal and block out other urban noise is by placing so-called reference channels or reference sensors into the setup as well. And so now the MEG sensors are here pretty close to the head, so they're really picking up the brain activity. But then we also place channels kind of out here, far enough from the head so that you're not capturing any of the brain activity, but you are recording all of the urban noise, or the environmental noise. So everything that kind of doesn't come from the head. And then in the data analysis, we remove from the data anything that correlates with the recording that we took of the environmental noise. Okay, you can see we have various decorations to make it more kid-friendly. So before we actually start the experimental session, we want to instruct the subject about the task that they're about to do, and it's better to do that kind of outside the magnetically shielded room so there's less distraction. So here these kids are learning about the task. And then the other thing that we need to do before we actually start the experiment is take a 3D scan of your head. And the reason why we do that is because oftentimes we don't necessarily have access to the person's, to an image of the person's brain. So an important part of MEG data analysis is that we actually localize the neuronal currents that are generating the magnetic field. So we have algorithms that figure out exactly where in your brain the magnetic field was generated. And we ideally plot that activity and do that analysis in the space of your actual cortex, so we would have an image of your brain. That may not always be possible, and so for that reason, we also take a 3D scan of your head, and then when we have that information, we're able to place kind of an average brain inside that volume, and it works pretty well that way as well. We also digitize certain points next to your ears and on your forehead as part of this procedure, and I'll explain to you why that is in a sec. So this process again is completely, doesn't even touch you. You have to be really still though. You wear a little swim cap so that we don't get a model of your hair. We're not interested in your hair. We're interested in the shape of your head. And here again, you have to be really still. And so then we're ready to go into the MEG machine. It's very important that once you're in the MEG machine, we know exactly where you are with respect to the sensor space. And so for that reason, we place little coils on your forehead and next to your ears on points that we digitized in the course of the 3D scanning of your head shape. And then we send a really sharp current, which you don't feel, well, it's not sharp current for the person, but something that's very easy for us to localize at the beginning of the experimental session. So you send a signal to these points. We're able to localize that signal very easily, and that information is connected to our model of your head. And that allows us to figure out exactly where you are. So that's what all these coils are. They're not actually making a brain measurement. They're allowing us to figure out where you are well, with respect to our sensors. Here's the boy getting his coils on. And now we're ready to slide into the MEG machine. Go really slowly. We make sure you're really cushy and comfortable. It's important that you stay still. If you move a lot, our data analysis routines get kind of messed up. So we assume that you're pretty still. We have various ways to give you stimulation. So now here we're very comfortable. We're able to monitor you in various ways while you're lying there, including we're able to track your eyes. So here's a display of our eye tracker. Sometimes it's useful to be able to combine the eye tracking data with the MEG data. So we're able to look at your eye movement, your pupil size, lots of different kinds of measurements. And we're able to visualize the fluctuations in the magnetic fields millisecond by millisecond with incredible temporal accuracy as you're lying in the machine. And then, of course, we save all that data and analyze it later with respect to whatever the question is that we're interested in. So I hope you've enjoyed this tour.